Imagine a particle so small, so elusive, that it can pass through 100 light-years of lead without even noticing. A particle that's everywhere, streaming through your body right now by the billions, but is so shy that it rarely interacts with anything. Meet the neutrino, the ghost particle of the universe, but don't let its size fool you. Neutrinos might hold the key to some of the biggest mysteries in physics. To truly understand neutrinos, we need to start at the heart of the stars. Our sun is a massive nuclear fusion reactor, fusing hydrogen atoms into helium. In this fiery process, energy is released as light and heat, but also as neutrinos. Every second, the sun produces about 10 to the 38th neutrinos, and they radiate outward in all directions into the cosmos. Right now, neutrinos from the farthest corners of the universe are traveling through you. But here's the mind-blowing part. These neutrinos don't just stop at the surface of Earth. Oh no, they go right through it, as if our planet wasn't even there. Right now, about 65 billion neutrinos pass through every square centimeter of your body every second. Feel anything? Nope. That's because neutrinos barely interact with matter. Our story begins in 1930, when the brilliant yet troubled physicist Wolfgang Pauli faced a mystery that seemed unsolvable. He noticed that when certain atoms underwent radioactive decay, they didn't conserve energy. Based on the mathematical calculations, energy was disappearing without explanation. In a moment of inspiration or desperation, Pauli proposed a bold idea, an invisible particle, one that carried away the missing energy without leaving a trace. He called it a neutron, later renamed the neutrino, or little neutral one. At the time, he even apologized to his colleagues in a letter.
I find myself compelled to propose a desperate remedy. This arises from the incorrect statistics of the N and L I6 nuclei, as well as the continuous beta spectrum, in order to preserve the law of conservation of energy.
He was convinced no one would ever be able to detect this ghostly particle. Little did he know, this wild idea would revolutionize physics. For 25 years, Pauli's neutrino remained a ghost story. No one could see it, no one could prove it existed. But in 1956, Frederick Rains and Clyde Cowan made history. Using a giant tank of water buried deep underground, they detected faint signals of neutrinos produced by a nuclear reactor. This discovery was so groundbreaking that Rains would eventually win a Nobel Prize. Pauli's ghost was finally real. Now here's where things get really eccentric. Neutrinos come in 3 flavors: electron neutrino, muon neutrino, and tau neutrino. But they don't stay in one flavor. As they travel through space, they oscillate, shifting from one type to another. This phenomenon is called neutrino oscillation, and it proved something revolutionary. Neutrinos have mass. This shattered the standard model of physics, which had assumed they were massless, and forced physicists to rethink about the fundamentals of our universe. But how do we study something so elusive? To detect them, scientists build massive detectors deep underground, shielding them from cosmic rays and other noise. Take the Super-Kamiokande detector in Japan. It uses 50,000 tons of ultra-pure water to catch the rare and faint flashes of light produced when a neutrino interacts with an atom. At the IceCube Observatory in Antarctica, thousands of sensors buried deep in the ice hunt for neutrinos that come from the most violent events in the universe: supernovae, black holes, and even gamma-ray bursts. Speaking of supernova, neutrinos were our first cosmic messengers in one of the most famous stellar events in modern history. When a massive star collapses in a supernova, it releases an enormous burst of neutrinos. In 1987, before the light from a supernova reached Earth, detectors picked up 24 neutrinos from the event, giving us an early warning and proving that neutrinos travel faster than the speed of light. Just kidding. They travel at nearly the speed of light, but got here first because they escaped the star's core before photons can. But neutrinos aren't just cosmic wanderers. We also create them here on Earth, in nuclear reactors and particle accelerators. These man-made neutrinos help scientists study their properties in controlled environments, shedding light on fundamental questions about the universe. Could neutrinos be the key to solving one of physics' greatest mysteries? Dark matter? While dark matter makes up 85% of the universe's mass, we still don't know what it is. Neutrinos have mass, but it's incredibly tiny, suggesting they could be part of a broader family of particles that help explain why the universe is structured the way it is. If this turns out to be true, neutrinos could help to solve this great mystery in modern science. In recent years, experiments like NOVA and DUNE have been pushing the boundaries of what we know about neutrinos. These experiments aim to answer questions like, why do neutrinos have mass? Could they help explain why the universe is made of matter and not antimatter? And are there even more types of neutrinos, like sterile neutrinos, waiting to be discovered? Every answer leads to more questions, proving that neutrinos are as mysterious as they are fascinating. Neutrinos are more than just ghost particles. They're storytellers of the universe, weaving together clues about its origins, its evolution, and its ultimate fate. They defy our understanding, challenge our theories, and inspire our curiosity. And that's why, as a tribute, we have named this channel Eccentric Neutrino. Like these particles, we aim to explore the unseen, embrace the unusual, and dive into the various eccentric corners. So, what's your take on these mysterious particles? Let us know in the comments. And if you enjoyed this dive into the world of neutrinos, hit that like button, subscribe to Eccentric Neutrino, and share this video with someone who loves the mysteries of science. Until next time, stay curious and keep exploring the unknown.